Imagine trying to give a large language model, like a whole library, maybe a massive code base or years of dense financial reports, or even a full medical history. And then you expect it to just know it all. Like asking, hey, based on these hundreds of thousands of pages, what's the biggest risk in AMD's 2022 10K? And how that different with Pepsi's? It's a super common need, right? We have these incredibly powerful models, but feeding them truly huge amounts of specific info. Well, that hits a serious wall. The standard way we do this now is in-context learning, ICL. You basically stuff the documents into the model's context window. It's pretty smart, actually, for getting specific info in and about retraining. But there's a catch, a big one. The memory cost of the key value cache, the KV cache.
That really is the heart of the problem. When you load up a long document, the LLM builds this internal thing, the KV cache. It's basically where it keeps track of the calculations for attention, how it looks back at earlier parts of the text. But the longer your input, the bigger this cache gets. It grows linearly. And a huge KD cache, that means huge GPU memory usage, which is, well, expensive. It's the major bottleneck. Limits how many people can query the same big document, limits how fast you can even start analyzing it.
Right. And that brings us nicely to the deep dive today. We're looking at a really interesting research paper. It introduces a totally new angle on this memory issue, using something they call cartridges, and these are trained using a method they've dubbed self-listdy. The big goal here, to give you all the power of ICL, letting the model act like it just read that massive document, but, crucially, with way less memory and much more speed. So our mission today, let's unpack cartridges and self-listdy. Really get in the nitty-gritty, the technical ideas behind them. Figure out why this could be a major shortcut to making LLMs handle real-world, massive data sets much, much better.
Okay, sounds good. Let's maybe first just double click on that ICL bottleneck. You mentioned it's powerful.
Yeah, because you just give it the text, right? The corpus. And the model uses that information. No need to fine-tune for every single document.
Exactly.
It's like handing the model a textbook and saying, answer questions using only this. But as it reads, processes the tokens, it builds up that KV cache. It's working memory for the input. For every single token it looks at, it generates and stores these key and value vectors. So if your textbook is, say, a 100,000 token financial report, that cache becomes absolutely enormous. Data for every token from the start.
And that's the pain point. Let's take that financial report example, like the AMD 10K the paper uses. It's huge. You want to ask lots of questions about it, maybe a specific number, then something about strategy, then summarize risks, maybe even a hypothetical. With standard ICL, every time you start a session with that document, you pay this big compute and memory cost just to build the cache. That's the prefill step. And while you're asking questions, that giant cache is just sitting there hogging expensive GPU memory, which limits everything else your server could be doing.
So, yeah, the problem is paying that hefty price memory and compute every single time you want the LLM to reference a big document. Now, here's where the paper gets really clever. What if you could process that huge document just once offline and create a tiny, super efficient snapshot of its knowledge, something you could load instantly instead of rebuilding that massive KV cache every time?
That is precisely the idea behind cartridges. It's not the full text, not even the full-size KV cache. A cartridge is a small set of learned parameters. Think of it like a highly compressed, intelligently trained representation of the document's key information, stored in a way the LLM can work with directly. And it's trained offline, specifically for one corpus, one document. Then when someone wants to ask about that document, you just load the pre-trained cartridge. The LLM acts as if it has the whole thing in context, but without that huge memory footprint from the original text's KV cache. It's a pretty fundamental shift, you know? You move the really heavy computation, understanding the document, away from the live, on-the-fly query time to an offline training step. You pay the cost once per document, and then you can potentially answer thousands, millions of queries very efficiently.
Okay, that makes sense conceptually. Moving the cost up front. And the paper talked about how they parameterize this, right? How they actually structure these learned parameters. They found that making the cartridge look structurally like a KV cache worked best, using something like prefix tuning.
That's right. Those specifically found that parameterizing it this way, sort of mimicking the structure the attention mechanism expects, was key.
Did they try other methods? Like, you hear a lot about LoR array for efficient tuning.
They did compare it. They looked at LoRR and other parameter-efficient methods. But for this specific job, distilling the essence of a long document into something small and queryable that preserves that ICL-like reasoning, the prefix tuning approach, the one that makes it look like a trained KV cache, came out significantly ahead. It seems like the structure matters a lot here, aligning the learned parameters with how attention works.
Got it. So you have this compact trained thing, the Cartridge. But how do you actually train it effectively? You can't just train it to predict the next word from the original document, right? The paper mentioned that just leads to rote memorization. It wouldn't be able to answer new questions well.
Exactly. That naive approach, just next token prediction on the document itself, fails. It learns to parrot, not to reason using the document.
So this is where self-study comes in, the secret sauce.
Precisely. Self-study is their clever training strategy to get around that limitation. It's basically an automated process. The LLM itself kind of studies the document. It generates its own synthetic questions and answers about the text, like the model creating its own comprehensive quiz on the material.
Ah, okay, so it's teaching itself about the document.
Yes, but the really crucial part is the training objective. They call it context distillation. Instead of just training the cartridge to spit out the right answers to those synthetic questions, which is still just predicting tokens, really, that it's trained to match the output probability distribution of the full model, the teacher model, when that model has the entire original document in its context.
Whoa, okay. So not just the answer, but the likelihood of all possible next words.
Exactly. It's matching the thought process, if you will, of the fully informed model. By aligning those probabilities across the whole vocabulary, the cartridge learns to capture the reasoning, the nuance, the ability to handle diverse questions that the full context model has. It's distilling the contextual reasoning capability itself, not just the raw text. That's the key innovation here.
That feels like a much deeper form of learning, and I assume they made it practical for really long documents, too.
They did. The self-study process generates a wide variety of questions, factual recall, structuring information, summarizing, even creative prompts based on the text. This makes the cartridge more robust. And crucially, they use a chunking strategy. They generate questions focused on smaller pieces of the document. This is essential for handling documents that are way longer than the base model's original context window could even handle.
Okay, so the theory sounds solid, the training method is clever. What about the results? Does it actually work in
Oh
practice?
yeah, the results are pretty impressive. When they compared cartridges trained with self-study against standard ICL on a tough, long context benchmarks, the quality was comparable, but the efficiency gains? Massive. The paper reports something like a 38.6x reduction in the KV cache memory needed during inference.
38 times less memory. Wow.
Yeah, it's huge, and that directly leads to much higher throughput on the server side. They measured a 26.4x increase in tokens processed per second when serving multiple users.
Okay, those are game-changing numbers for anyone trying to deploy these models at scale for long document tasks.
Definitely. Major improvements in practicality and cost effectiveness.
And you mentioned it can handle documents longer than the original context window.
Yes, that's another really cool outcome. It effectively extends the model's reach. They showed, I think, a 128K context model being able to effectively work with a document over 480K tokens long just by using a cartridge trained for it. So you're not just compressing the knowledge representation, you're sort of bypassing the original context length limit.
That's amazing. And then there was this composability thing you mentioned earlier, which sounded almost too good to be true. What if you train one cartridge on the AMD report and a totally separate one on the Pepsi report?
Right. This was a fantastic result they showed. You can just take those two independently trained cartridges and literally just concatenate them, stick them together at inference time, and the model can then answer questions that need information from both documents without any extra training on the combined data.
No joint training needed, just stick them together.
Just stick them together. It's incredibly powerful for scenarios where you need to synthesize info from multiple sources. Think multi-document analysis, building knowledge graphs on the fly.
That composability feels huge for real-world use cases where info is rarely in one neat file, And how easy is it to actually deploy these cartridges?
It seems quite practical. Because they are structured like parameterized KV caches, they fit quite naturally into existing LLM serving systems. Those systems are already built to handle KV caches for different users or requests, so integrating cartridges should be much smoother than methods needing entirely new server architectures.
Okay, so it fits into the current infrastructure relatively easily.
Now, it's worth digging just a tiny bit into why this works so well. Why does training this specific kind of representation, this parameterized KV cache, beat simpler approaches? The paper's appendix gives some hints. Think about trying to recall information from a really long text. It's like finding a specific fact linked to a keyword, right? Associative recall.
Yeah.
Simpler methods for long context, like some linear attention variants, often use a fixed rule to update their internal memory state. They just sort of add up the information for each key value pair as they see it.
Okay, like a running tally.
Kind of, but that simple additive process runs into trouble if the information is messy. What if the same keyword appears multiple times with different meanings or associated facts, or if different keywords are very similar? This additive approach creates interference or noise. When you query, you get a muddled answer influenced by all those similar or repeated keys. These simpler methods struggle to pull out the right piece of information.
Okay. They get confused by the noise.
Exactly. The theory suggests that training the KV cache parameters with gradient descent gives the model something more powerful. It learns how to process the incoming information in a way that can actively disentangle or peel away the interference from confusing bits it saw earlier. This learnability to handle the noise and retrieve the correct information accurately, even in a very long and complex sequence. That seems to be why training this specific structure works so well for long context recall. It's more robust than a fixed update rule.
That makes a lot of intuitive sense. The training lets it learn to navigate the complexity, not just follow a simple rule. But training takes time and resources, right? What's the cost?
Good point. There is an upfront cost. Training a cartridge isn't instantaneous. The paper mentioned around 30 minutes on a pretty beefy setup, like an 8x100 node, to train one for a model like Llama 8B. So yes, that's definitely more compute than just doing one prefill for one user with standard ICL.
Right. But, and this seems crucial, that training is done offline and only once for that specific document.
Exactly.
If you're dealing with a company report, a code base, medical records, things that get queried over and over by potentially many users, that initial 30-minute training cost gets spread out, amortized over maybe thousands or millions of much cheaper, faster inference queries later on.
Precisely. The per query cost drops dramatically because of the memory savings and throughput increase. The upfront investment pays off if the document is used frequently. And think about the applications this unlocks. Things that are just too expensive or clunky today, like a medical AL that can instantly access and reason over a patient's entire medical history, not just a summary, or coding assistants that actually understand the whole massive code base they're working in. Chatbots with genuine long-term memory spanning many conversations, cartridges and self-study could make these kinds of powerful data-heavy AI applications much more realistic and affordable.
So wrapping up our deep dive here, cartridges trained with self-study look like a really promising path forward. They offer a way to get those ICL benefits for huge documents, letting the model act like an expert on them, but slashing the memory cost and boosting the speed by using this clever offline training approach to create a compact representation.
Yeah, the key takeaways are really that trained, parameterized KV cache idea, the self-study approach with context distillation to make sure it reasons correctly, and that surprising, really useful composability feature.
Definitely. And maybe a final thought for you, the listener. How might this change things? This ability to give an LLM cost-effective access to your specific massive knowledge bases, internal documents, archives, specialized data. How could that fundamentally shift how you interact with AI, making it a true expert tailored just for the information you care about most? Something to think about.